So today we'll discuss about a very important part of the calculations that we are starting for the atmosphere distillation column, that is the product distillate yields. That is the first step in calculation of the atmosphere distillation column. So in this one, basically we are going to design the atmosphere distillation column using the crude oil that is given here. The crude oil is from the Venezuelan crude oil and the field name is the Ajuana. So we are going to produce these four different products: light naphtha, heavy naphtha, light distillate and heavy distillate. Their name in shortcut name: light naphtha LN, heavy naphtha HN, light distillate and heavy distillate HD and LD. And you can also designate that one D1 and D2, D3 and D4. Also you can designate the top product, that is from the top of the column we recover the light naphtha, and these three, one heavy naphtha, light distillate and heavy distillates, are basically sorry, the side products. So let us know represent all these things in the graphical phase. For example, this is the distillation column, atmosphere distillation column, and these are the trays that is showing here. So the feed that is entering at the very bottom level of the column, and we can get the first product, light naphtha, from the top. Then this is the side products, heavy naphtha, then light distillate and then heavy distillate. Then the remaining is the bottom, that is the residue. So residue is not taken as a product. All these four streams are taken as a product. This is called the total distillate. This is summation of D, that is total distillate. So total distillate is nothing but the light naphtha plus heavy naphtha plus light distillate plus heavy distillate. If we are talking about the yields, total distillate, so yield of light naphtha plus heavy naphtha, light distillate and heavy distillate, all these things basically can be represented here. Now let us look how these values or these products are showing in the curve. Basically we are going to give about the basic understanding of representing all these curves in the TVP one, all these products in the TVP curves. So this is a very important thing, you have to listen carefully and understand it. For example, if there is a whole crude, then what happened? This is the TVP that is representing the whole crude, and if this is obviously one initial boiling point and one final boiling point, because there is a one curve. And if we have a two cuts from this whole crude, cut 1 and cut 2, then this can be represented by cut 1 and cut 2. That's a slight difference between these two cuts. Although the crude oil is same, but that is divided into two parts, their nature is now changed. We have a two initial boiling points and two final boiling, means cut 1 have their initial boiling point and their final boiling point, cut 2 have their initial boiling point and their final boiling point. Similarly, if suppose we have a three cuts, so that can be shown like this one: initial boiling point of cut 1, then final boiling point, initial boiling point, final boiling point, initial boiling point and final boiling point. So that is a very important observation here that you have to look carefully. Now again represent the same thing for the two cuts in some larger scale. For example, this is our TVP whole crude, and if we want to cut down in a two parts, so it looks like cut 1 and cut 2. The important thing is here basically for this cut 1 and cut 2 that you should know the values in the TVP curve, the meanings of different cuts basically. For example, cut 1, that is a lighter one because they have recover at a very low temperature as compared to the cut 2, number one thing. So lighter cut, a light cut, and that cut 2 is a heavy cut. The second important thing that you all should know is basically, as I have already discussed about the initial boiling point of cut 1 and final boiling points. So this is a light component, final boiling point, and we are basically much more concerned about these two one, and heavy components, initial boiling points. So this point and these 2 points are very important. The second important thing is that although their values are different in the y-axis is the temperature values, their temperature values are different, but that temperature relationship is important here. Relationship means the light component final boiling point, although that is a light one, but their final boiling point temperature is greater than the temperature of the heavier components initial boiling point. That relationship is very important. Always the light component have the higher boiling point as compared to the initial boiling point of the heavy cut. That is the one thing. Second thing is that on as far as the x-axis is concerned, that is a volume percent. So in the x-axis, when the one cut is completed, because it is a volume percent, for example cut 1 is up to the 35%, so just after that the next cuts will be started, means one cut is ended here at 35 and second cut will be started from 35 onwards. So that is the important thing here, and this term is known as the TVP cut volume, and that is same for both things. That you have to understand. That is a volumetric yield point between the two fractions. Fraction 1, that is the cut 1, fraction 2, that is the cut 2. So the cut volume, TVP cut volume, is the value from which the first cut is ended, first cut is completed, and the second cut is started. So that is the one term that you should understand their physical meaning, their representation in the graph. Now the second term that you need to understand after TVP cut volume, that is basically the definition of light component. We have discussed about the light component. So mathematically we can represent this one by T100L, means the lighter cuts when it is completely vaporized, 100% of the lighter cuts, the temperature at which 100% of lighter cut is vaporized, so that is called the light cut temperature. We can get the value from the y-axis. Similarly, for the cut to initial boiling point, that called the T0H, means the initial point of the heavy cut. So you also understand the mathematical terms of these two things. Okay, if you understand these two things, so the difference between these two values are very important thing, and this difference means the final boiling point of light, this minus this difference is called the TVP overlap. So this is the second term that you should know after the TVP cut volume. TVP overlap is nothing but the difference between the temperature of 100L minus 0H. Okay, and the final boiling point of the light component minus initial boiling point of heavy cuts. That is the important thing, TVP overlap, because we are going to use these terms in our calculations. Now come to the next point. Next point, let us take the example of TVP overlap. For example, this is 250. The second cut's initial boiling point is 250, and final boiling point of the lighter one is 200. Sorry. 250 is the final boiling point of light cut, and 210 is the initial boiling point of heavy cut. Then what will be the TVP overlap? So TVP overlap can be calculated 250, this value minus this value. So that the difference, it comes around 40 degree Celsius. So in this way we can find out the TVP overlap. Now come to the next important point, that is a TVP cut point. That is a new term that you have to remember here. TVP cut point is the half of the TVP overlap, that this value, this is a TVP overlap, half of the TVP overlap plus the initial boiling point of heavy cuts. And how we can represent this thing into the graph, this is the basically, if suppose this is a half point, so this is nothing but the TB mid volume percent of TVP overlap, and this value on y-axis is known as TVP cut point. So let us take the example again. TVP cut point for the same case to 210, that is the initial boiling point of the heavy cut plus the difference, that is the TVP overlap, difference between temperatures, divided by 2. So 40 upon 2 is 20 plus 210 is for 230 degrees Celsius. So at 230 degrees Celsius, this is the TVP cut point of this fraction between these two fractions, and corresponding to that we can find out the TVP cut volume. So these are the very important terms. We can again show you these terms: TVP cut volume, the volumetric yield point between two fractions, TVP cut point, TVP temperature corresponding to a TVP cut volume, that can be represented, calculated by this one, and TVP overlap is nothing but the temperature difference between the lighter final boiling point of lighter to the initial boiling point of heavy cuts. So these three are the very important thing. You all should remember this one for our calculations. So our target is to find out the yields of these cuts. How we can find out? For example, this is a TVP curve. So these are the steps. First we have to find out the TVP overlap, After that we have to find out TUP cut point with the help of TUP overlap, and then with the help of TUP cut point we can find out the TUP cut volume, and that TUP cut volume basically give the TUP cut volume is give the yield. For example, this is a TUP cut volume and on the y-axis, and this is x-axis TUP cut volume, and that give the yield value. So our target is to find out the yield of each and every cuts that we want to produce from the given distillation column. This is a one theory, and the second part of this one is a very simple one. Few recommendations are available, few tables for recommendations are available with us. For example, one recommendation is the ASTM boiling ranges. We have by default some ASTM recommendation values of ASTM boiling ranges of light naphtha, heavy distillate, light distillate, heavy naphtha, and all these values. So we have different endpoints value. Basically their boiling ranges in terms of endpoints are given here. So that is the one recommendations. The second recommendations is given for the separation criteria. For example, if we want to separate the light naphtha with the heavy naphtha, then these are the ranges of the separate gap 595. If we want to separate between the heavy naphtha to light distillate, these are the values, recommended values, plus 525 to plus 50. Light distillate to heavy distillate we can take these 0 to plus 100. So these recommendations, with the help of these recommendations and the concept that we have discussed, we can find out the yield. So this is a problem to find out the yield of the material basically, and these are the basically given values. ASTM endpoint of all these four products are given: light naphtha, heavy naphtha, light distillate, heavy distillates. Gap values are given here, and with the help of these two values we have to find out the yields of each and every fractions. So we'll discuss in the next slide. Thank you.